Hello and welcome to the video lecture accompanying lecture 28, where we're covering sections 29.1 to 29.6 and specifically looking at half-lives, radioactivity, rates of decay, and so on. These are going to be the numerical problems from chapter 29. If you want to look at some conceptual examples and conceptual discussion from chapter 29, please look at the video lectures that accompany lecture 27, where I go over the background and key terms. Okay, so in this case, we're going to get into the key formulas. And please disregard this typo. I obviously have the wrong section numbers there, but the header is correct, 29.1 through 29.6. With a focus on whatever section it is that covers radioactive decay, which I don't have the number in front of me. Our one objective is to learn how the decay rate of radioactive substances depends on time. Okay? And I'll show you one other example. I'm going to do 3 examples. This is just going to be a brief video to just get a little bit of extra exposure to the numerical process of solving half-life problems. Okay? So the first thing we want to look at is the mass of an alpha particle. All right, so the mass of the alpha particle is almost exactly 4 atomic mass units. It's a little bit greater than 4 atomic mass units, namely because the nucleons of a helium atom are a little bit heavier than the nucleons of a carbon atom, but more on that when I cover the concepts in chapter 30. Okay, that just has to do about where fusion produces energy and where fission produces energy. Okay, but the point being is that this is the mass, about four nucleons worth of mass, if we're considering each nucleon has an atomic mass unit of about 1. Okay, but of course it's not exact, and that does matter. Okay, now we're going to see that in the first example. That wouldn't be in every half-life problem, that wouldn't be exactly relevant, but it can if we're concerned about conservation of momentum or conservation of energy. That's where you would see that mass as a relevant value. The 2 big equations that you would see in numerical examples of half-lives and radioactive decay are the following. The first is the number of remaining nuclei. So this is n, simply a number as a function of time, that's function notation. And so the number of remaining nuclei is equal to the number of initial nuclei in a sample multiplied by e to the negative lambda t. All right, so this is an exponential decay function. It's dependent on time, and we'll talk about what lambda is in just a second. But the point is that the number of remaining nuclei, even if we don't know what lambda is or its value, we do know that this is telling us that we have an exponentially decaying number of nuclei. Right? That's the idea. The population is exponentially decaying for any radioactive substance. Okay? Our next equation is quite similar, and this is the activity rate, because it turns out that the activity rate exponentially decays as the number decays. And that's because any given nucleus has a certain probability of decaying. If there are less nuclei in the overall population, then there'll be less decays per unit time. Okay, so this could be decays per second, or any other rate that would be specified in the problem. Okay. Obviously, we saw a couple of key examples. For example, we had the Curie, which was 3.7 times 10 to the 10 decays per second, and then the Becquerel, which was just 1 decay per second. Okay, so those are kind of the 2 standard units, but sometimes it might just be specified as 1,000 decays per second, which isn't in units of Becquerel or Curie. It's just in units of decays per second. Okay. So a little bit about that, but make sure you check your units or what's specified. Now, what about time? Okay, well, the mean time, it turns out, is just a reciprocal of the decay constant. Okay, so the decay constant has importantly has units of inverse seconds. So it is not a time, unlike half-life, which is this here. Okay, half-life has units of seconds, but the decay constant does not. Okay, it's an inverse time. It's a rate. It's a frequency, essentially. So the mean time, that's the mean time it takes for any individual atom to decay, is simply 1 over the decay constant. But the half-life is not exactly related to the same way. So in other words, the half-life and the mean life, if we can think of that, are not equal to each other. In fact, the half-life is about 0.693 times the mean life. So it's about 69 or 2/3 as long as the mean life. So mean life is always longer than half-life. Okay. Now, half-life is a very go-to result, more so than mean life, because it is kind of strange to think, oh, well, now 69.3% of the original population is remaining. That's not a number that sticks in your head. thus the popularity and the commonality of discussing things in half-life. Because if you have a sample and half that sample is left, that's a very easy thing to visualize and to imagine. Okay? So that's why you see half-life so much. Not because it's mathematically superior or anything, it's just kind of quicker to wrap your head around. So let's take a look at example 1. So this is not the one where we talk about decay rates or activity rates or anything like that. We're just going to talk about a decay, but what that means in terms of the momentum and energy of the product of that decay. So we have uranium-238, a well-known radioactive material. I give you the atomic mass of uranium-238, okay? And I will tell you right away that it decays into thorium-234, and here is the atomic mass of thorium. It's going to do that decay through alpha decay, okay? If we think about it, that actually makes perfect sense because our atomic mass, because that's whenever you see a element listed like this, the 238 is the atomic mass. That would be the N value. Yeah, actually, no, sorry. N value is the number of, just being consistent with the terminology in your book. N, of course, is the number of neutrons, so it's not N. It should be, let's see, so we have, it's A, okay? So A, this would be the value A. Okay, that's the letter that's used. So that's the atomic mass number, as opposed to the element number, which is Z, which is the number of protons. And so, for uranium, I don't know what it is off the top of my head, what the atomic number as opposed to the atomic mass of uranium is, but it's certainly not 238, because this includes a lot of nucleons and only maybe, I think, 80 some protons. But again, I don't remember the atomic number off the top of my head for uranium, let alone thorium. But the important thing is that the atomic mass reduces by 4, because that's exactly what we should see every time we see alpha decay, because alpha decay carries with it 4 nucleons, 2 protons and 2 neutrons, which means the atomic mass will always reduce by 4. What is the velocity of the emitted alpha particle, and what is the velocity of the thorium atom? So we're going to find the velocity of both products, because uranium in this case is becoming 1 alpha particle plus 1 thorium atom. So, they're both particles in a sense, all right? And those two very, very tiny things are going to go off with different speeds. And we can find those speeds through simple conservation of momentum and energy. So let's run through it. So the first thing we're going to do is find the total kinetic energy. And this is going to be the change in the energy of the system. We're going to find this using E equals mc squared, E equals mc squared, and relating the change in mass to energy, right? Because here's the original uranium. This is what the uranium is becoming, the thorium plus the alpha particle. And then we're multiplying by the relationship between mass to energy. Okay, so we're directly relating mega electron volts to atomic mass units. Okay, and so that turns out that through this process of radioactive decay, we have a net gain of 4.27 mega electron volts. So we have less mass, thus that mass had to become energy, and we're assuming then that energy is going to become the kinetic energy of the two products. We're not assuming any of that energy is going to become pure photons. We're assuming all the energy is going to become the kinetic energy of the thorium and the alpha particle. Okay, and momentum is going to tell us that we have P initial equals P final. The uranium atom is at rest in its own reference frame. The two products, the thorium and the alpha particle, TH for thorium, alpha symbol for alpha particle, well, they're going to have to sum up to be the final momentum, P final, okay? So P for momentum. That means that in magnitude, P thorium must equal P alpha. Okay, well, if we think about it, that means that 234, 0.04306 atomic mass units times the velocity of the thorium has to be equal to the much smaller 4.002603 atomic mass units times the velocity of the alpha particle. Okay, well, that's going to tell you that the velocity of the alpha particle must be much greater. Okay, and indeed, it is conservation momentum that always points to the smaller product of the radioactive decay being the faster one. Energy alone wouldn't tell us that. Okay, and so then we can find that the velocity of the alpha particle is going to be 58.5 times faster than the velocity of the thorium atom. Okay, so now it's simply a matter of then taking the combined kinetic energies of the two products, the mass of the thorium, velocity of the thorium, mass of the alpha, velocity of the alpha. Of course, this is kinetic energy, so we have to remember to square them. Although here I wrote the wrong symbol. I wrote alpha, but I meant to write 2, of course. All right, you can see that later on I wrote 2 correctly. And this energy has to be the same energy that we solved for from the missing mass. All right, so this is an E equals mc squared. This is the mass becoming energy, and then that energy becoming kinetic energy. Okay? So we're going to go ahead and work that out. I'm going to go ahead and then just do a substitution. So I'm going to substitute out the velocity of the thorium. That way I only have one unknown here. This is the velocity of the alpha particle. And then I'm going to relate it to my units here. This is my mega electron volts, which is why it's times 10 to the 6. And this is just the conversion to joules. I want to convert it to joules because that way it will give me the velocity of my alpha particle in meters per second, which I go ahead and do. And there we go. So we have a velocity of the alpha particle of 1.01 times 10 to the 7 meters per second, which is less than 1% the speed of light. So we're basically good with non-relativistic considerations here. All right. And all right. So that's it. And let's see. And I never went ahead and solved for the velocity of the thorium atom, but you could easily just divide that number by 58.5, and that would give you your V thorium. Okay. Okay, so hopefully that approach makes sense. You can look at the notes after the fact, and I'll remember to fix that alpha to a 2. Okay, all right, so I already started showing the steps here, but I wanted to talk about example 2. All right, so in example 2, we have a radioactive source that has a half-life of 1 minute. At time t equals 0, it is placed near a detector, and the counting rate, the number of decay particles detected per unit time, is observed to be 2,000 counts per second. Okay, so there's an example where I don't give you the units in terms of Curie or becquerels or anything. I just tell you it's 2,000 counts per second, but that's sufficient. Okay, and then part A, find the mean life and the decay constant, and then find the counting rate at time equals 1 minute. Okay, and 10 minutes. All right, so what we're going to do right away is we're going to go ahead and let's see. So we're told we know the half-life, all right? So, and we know that our initial rate is 2,000, and this should be A. That's the unit that we're using for the rate. You can think of R for rate, but your book uses A. Okay, so I want to use A as the activity. Think of it as it's activity rate, or so it's either A or R, but we're going to use A to represent activity rate. So again, the initial, look at the subscript, is 2,000 counts per second. Okay, so since we know the half-life, we can easily find the mean life, which we were asked for, and it's just 86.6 seconds. That makes sense, right? Because it's just a little bit larger, right? Okay, and then we can also easily find our decay constant, and it's 0.012 hertz. All right, in this case, it's a relatively large number because our half-life is quite small, right? This isn't the half-life of thousands or millions of years, okay? Which, of course, then the frequency would be much, much smaller. Okay, so then in part B, let's go ahead and find those activities at other times. So once we have lambda, right, importantly, because all the exponential functions are written in terms of lambda, it's really quite easy. We just plug in the initial activity rate. Here I've correctly identified as A sub naught. And then we put in e to our negative lambda, there it is in hertz, multiplied by the elapsed time, and we were told it was going to be 1 minute. We want to make sure it's in seconds because, of course, lambda is in inverse seconds, and we need those units to cancel out. And it turns out that we end up with 1,000, all right? Okay, so what's that telling us? Well, we have a half-life of 1 minute, and we had our rate go down from 2,000 to 1,000. Oh, okay, so it turns out that half-lives exactly correspond, well, since they are the same exponential decay function, to activity rates. So if your population decreases by half in a certain amount of time, your activity will also decrease by half in that same amount of time. In this case, 1 minute. And then if we after 10 minutes, well, it's not going to be a tenth, but it'll be much less than that because it's exponential. So we're going to plug in 600 seconds. We just plug in the same function here, but instead of 60, of course, it's 600. And we end up with a activity of 1.95. And again, this should be A. Okay, so it's dramatically fallen off. That's the nature of exponentials. So I've left a couple more for your practice, just to, if you want to get some more practice besides the ones in the study guide. And the last thing I want to show you is just a little bit about counting the atomic number and atomic mass for radioactive decay. It's a little bit more of a concept question, but I figured I'd put it in here anyway. All right, so example 5. The figure shows part of the decay scheme of Neptunium-237 on a plot of mass number A versus proton number Z. 5 lines that represent either alpha decay or beta minus decay connect dots that represent isotopes. Okay, so this is beta minus decay. That's the type of K that produces, or type of decay that produces electrons, okay, and antineutrinos, okay, again refer to the previous lecture videos for that. What is the isotope at the end of the 5 decays? So what we can do is we can kind of piece things out here. So we know that here, if we're going down in both atomic mass and atomic number, then this section right here must be an alpha decay. It can't be anything else because it's the only thing that would be decreasing in both. And that means we had to go down by a step of 4, so it tells me that that line must be 233. Likewise, this is another alpha decay, and so then I have to go down by another 4 to 229. Again, that's atomic mass of 229. Meanwhile, what's happening with the atomic number? Well, if you look on the periodic table, you can find out that Neptunium has 93, so it has 93 protons. When we do our first alpha decay, we're going to go down 2 to 91. Okay, so this one right there is 91. Then, well, what's this? What does this represent? This to this dot to that dot. Well, that's got to be beta minus. Why do we know it's beta minus? Well, because when the nucleus gives up an electron, it turns a neutron into a proton. That actually keeps the atomic mass the same, hence horizontal on our atomic mass versus atomic number graph, but increases Z by 1 because now we have an extra proton. That's exactly what we see. Okay, so we know that this is beta minus. All right, so now so far we've got alpha, beta minus, another alpha. All right, let me just put these in here. Beta minus, another alpha. And we can tell we have another alpha here, and then we know this one also must be a beta minus. Okay, and so then as we work it out, we get down to 89 as our final result in terms of our number of protons, our Z number, our atomic number, and our final atomic mass is 225. That's the total number of nucleons. And that tells us that we have actinium-225. And we just look up actinium because it is the 89th element with 89 protons. And the 225 is simply by making sure we subtract a total of, well, 4, 4, 4, so 12 atomic mass units. All right? And again, the atomic mass number is not exactly the same as the atomic mass because we know that nucleons have different weights depending on their relative location on the periodic table to iron. And so that's why there's always those decimals afterwards. But to a good approximation to an integer, you can say, yeah, the atomic mass is about 225, but those extra values matter. But here we're talking about the atomic mass number after all, 225. And this is a naturally occurring trace isotope with a half-life of about 10 days, incidentally. Okay, and this is how we'd write it. This is the notation with the up here the A number and the Z number, and we could calculate N by just taking 225 minus 89 would equal N, the number of neutrons. Okay, all right. Well, thank you so much for watching this video lecture accompanying lecture 28. And there's one more this semester. I'm going to publish a video today as well for chapter 30, where I'll talk about some of the concepts of chapter 30. But that's all you're going to be responsible for. No actual numerical examples from that entire chapter. All right, so thanks again for watching.